All right, so I think now we're on the recording. We've made all the class announcements. Lab, this is Respiratory, March 2nd, Tuesday's lab, Bio 139. And we just started doing definitions. So we will, I'll throw this up on for you guys to read.
I'll throw this up on.
All right, I'm trying to figure out why I'm hearing myself. Is that one of you all?
Someone has their mic on.
You guys might have to go in and find who accidentally has it on and just mute it.
I might have to go in and find who accidentally has it on and just mute it.
Diana Thompson.
Well, sorry, Diana, you just got called out. All right, cool. Cool. All right, so tidal volume. Now, this is the volume that enters and leaves with each breath, okay? From a normal quiet inspiration to a normal quiet expiration. So we're just sitting there breathing, relaxing, and listening to me. So that's about half a liter of air. Now, tidal volume will change with the pattern of breathing. So if you have shallow breaths or deep breaths, obviously this changes the tidal volume. For you pregnant mothers or has been or future pregnant mothers, your tidal volume actually increases when you're pregnant. If you think about it, you have a fetus on board that requires oxygen, so that takes away from the tidal volume. All right, I'm going to try to slow down. I don't want to rush. Inspiratory reserve volume, IRV. Guys, these are just flashcards, so we're going to go over them and you just spend your time doing your flashcards. So this is the extra volume that can be inspired above tidal volume, okay? So, you know, we take a normal breath and then all of a sudden we take a little bit more breaths, like that's the reserve, right? And so this is extra volume that can be inspired above tidal volume. From normal quiet inspiration to maximum inspiration. So I'm over here and I'm breathing, and then I can take a little bit more breath. That second breath is the inspiratory reserve volume. And this kind of relies on the muscle strength. There's a term called lung compliance, which is kind of like the elastic recoil of lungs. I don't want to go too much into that. That's just what happens if some people who the lack of lung compliance comes from people who have smoked almost their entire lives. This is how we get emphysema, is when the lungs lose the recoil or the elastic recoil in the lungs, and it kind of flails the chest out. And when the chest is increased outward, then it's really hard to breathe in even more. So this is about 2.5 liters of average value on your inspiratory reserve volume. So that's the extra volume that can be inspired above the tidal volume, from normal quiet inspiration to max inspiration. Okay, residual volume. Residual volume is basically the volume remaining after maximum expiration, okay? So even though we blow everything out of our lungs, like, you know, we literally contract our intercostal muscles and breathe everything out, we still have some reserve left over. And that is about 1.5 liters. Now this will rely on muscle strength of your intercostal muscles and the resistance in your airway. All right. This is also your inspiratory reserve volume will be reduced in pregnancy, obesity, COPD. This is obstructive compulsive pulmonary disorder, or any kind of tracheal or bronchi obstruction. No, excuse me, cross that out. I was reading something else. I'm reading expiratory reserve. No, I'm sorry. Yeah, that is the expiratory. I apologize. The expiratory reserve is the extra volume that can be expired below tidal volume from normal quiet expiration to maximum expiration. I read the wrong one. All right, so let me clean this up. Expiratory reserve volume. That is the extra volume that is expired below the tidal volume. That's the same kind of concept I had where you completely blow it out. And that is from normal quiet expiration to the maximum expiration. And that same thing, it's about 1.5 liters. And that relies on the muscle strength and the low airway resistance. I never cared for respiratory when I was in your all seats. Just never did. I don't know why. Okay, but that doesn't mean you all can love it. Residual volume. Let's go over that one. That's the volume remaining after max expiration. So that's probably the one I read off earlier. Volume remaining after max expiration. You cannot get rid of the residual volume. The expiratory reserve volume, you can. This is you cannot, and it cannot be measured by any spirometry, which is a method of how we measure lung capacity. Okay, let me check the chat real quick, make sure we're okay. Yeah, Liz, it's being recorded. Sorry, Derek, I just added you. I just saw it, my bad. All right, so we're caught up on the chat. Okay, so total lung capacity, otherwise known as TLC. Total lung capacity is basically everything, right? So this is the volume of air in the lungs after maximum inspiration, maximum inhalation. All right, that's the sum of all volumes. Total lung capacity, TLC. 6 liters of air is normally held within the lungs. All right, and then the vital capacity, that is the volume that can be exhaled after maximum inspiration. So we inhale, we fill up our lungs with air, and then we completely blow it out. It's like taking one big deep breath. That's the vital capacity. All right. So that's going to include the inspiratory reserve volume plus tidal volume plus expiratory reserve volume. So if there's going to be a calculation on any quiz or test, there's your calculation for vital capacity. The average is right around 4.5 liters. This is the one that often targets, that is often targeted by pathological states, i.e. COPD, emphysema, probably COVID too. I think I saw a picture of a study that they did from somebody who has had COVID and subsequently succumbed to COVID versus a normal lung. The normal lung was nice and pink, the way it should look. The COVID lung, you could probably Google these images on Google Image. The COVID lung was fibrotic. It was very white, pus-filled. It was inflamed. You could see discolored. And that is just, that's what a lung look, that is a diseased lung. It's not exactly a diseased lung as in like smoking. Smoking would have more like a black tone to it, or like a black patina. This, however, is just inflamed, purple, white, it just looks ill, more fibrotic. So the vital capacity is often the one that is measured in a hospital setting that will, that usually is affected by disease. Okay. And that's about 4.5 liters. Okay. So down here at the bottom, label the chart below using the following term: tidal volume, inspiratory reserve, expiratory vital capacity, and residual volume. I think the next page on page 55 has those answers. Okay, so that's just probably something that would probably show up on a quiz or an exam, and it would ask you to label each one. Now, there's a question here that's going to ask you to solve patient's lung volumes are the following. Oh, the IRB. So if you can probably do this on your own time, because it gives you an example or the equation there. All you have to do is manipulate it and solve for IRV, and that shouldn't be too hard for you guys to do. Okay, let's see.
What's the equation for IRV?
Hold on, I just sorry, I just had to add somebody. IRV. So we would probably, what would you do? You would manipulate it. So what I mean by that is you would probably just do some good old fashioned algebra. In this case, you would probably stick vital capacity on the other side, and then you would minus off expiratory reserve and minus off total TV. Which is that? Total TV is tidal volume. So I think VC, IRV, what is it? RV plus ERV plus total capacity. TV. Thanks. Okay, so if we're going to solve for IRV, then I'm going to take IRV is equal to minus ERV minus total volume minus vital capacity. I think that's what that looks like. It's a lot of minuses, though. We're not going to be doing any division. Let me revisit that and see. Calculate the patient's IRV. Raymond, how'd you do that? Did you minus everything off? That's what I have on the board. Raymond's got 2,900. So if you just use the algebra part, that's what I did, but I'm not sure if that's correct. Yeah, the normal equation. Okay, that's what I did too. Yeah, okay. Okay. Just seems high. But if it's 6,000 liters and you're at 2,900 liter, or is it 6,000 milliliters and you're at 29 milliliters, then it's probably true. Because the total lung capacity is going to be 6 liters, would be 6,000 liters. So, and if you notice that it's calculated in milliliters. Okay. All right. So does everybody follow that? We good? Yeah. Thank you, Irina. Yeah, it is. It's just a lot of subtraction. All right. Make sure. Okay. Yeah, it even threw me off for a curve. All right. So can you guys see that? That's the right one. It should be 2,900 milliliters or 2.9 liters. All right. So now these next few pages, we're going to skip over because this is what would happen if we had this all set up and, everybody be back in class. Not this semester, however. Okay. So with even through 57, we can't do these. I'm trying to see if I can even make them up. All right. Yeah. Okay. Yeah, that's right, Raymond. I'm following you on the chat now. Okay, guys, let's go down to 58, page 58 in protocol 2. I want to introduce a concept called minute ventilation. All right, now minute ventilation is something that we kind of goes hand in hand with cardiovascular system, okay? And I'm trying to look through my notes right now so I can explain this correctly. So this is the amount of volume in mils that are inhaled over a minute. All right, so this is probably the tidal volume and the respiratory rate that is multiplied. All right, so tidal volume, as you can see there, the VE, that is the minute ventilation, is equal to tidal volume times breaths per minute. Breaths per minute are probably going to be around 12, right? 12 breaths per minute. And then your tidal volume, what did we say that was? Was that like a half a mil, I think? Or a half a liter? Yeah, 500 mils, right? So we're probably going to be about, normal would probably be about 6 liters per minute there. All right, now that's kind of interesting. That's how we kind of, that'll change with exercise or resting, is the minute ventilation. So if our total volume at the top of protocol 2, if our total volume is 500 mils, all right, our frequency is 12 breaths per minute. I really want to change that to, I want to keep it in liters. So, but we'll just keep it in milliliters. It would be 500 times 12. What is that? 6,000, excuse me, 6,000 mils per minute, otherwise known as 6 liters per minute. So let's highlight that and make sure we understand that. I'm trying to see what else we can do. I'm going to shut that door now. Okay, sorry, I had to shut the door. Okay, so now, so let's pretend we are exercising, right? This is kind of go down the prediction. Please write down what you think would happen in the frequency, tidal volume, and minute ventilation in response to exercise. Will increase, decrease, or stay the same? So, excuse me, the frequency of your breaths are obviously going to increase, right? It's the same thing with like cardio output. Your frequency is going to increase, your tidal volume is going to increase, and your minute ventilation is going to increase. Okay. Now it says measure frequency and tidal volume. Well, yeah, we can. So at the bottom of page 58, it says what happens to the frequency and tidal volume with exercise? Well, they're going to increase. You have more oxygen demand on your muscles. Therefore, your pH in your blood will be sensed by the baroreceptors in your blood, which sends signals to your respiratory center in your brain to begin inhaling and exhaling at a higher rate. It's all based on your pH of your blood, really. Because if you have more demand on your muscles, then you create more acid in your blood, and that's how the respiratory center can sense this. Okay, it's in the pons and medulla of your brain. All right, so breathe normally for 2 minutes and inhale. Now measure how long you can hold your breath. Record this. Breathe normally for 2 minutes and exhale. Now measure how long you can hold your breath. We can't do any of this. If you inhale deeply before holding your breath, do you have the urge to inspire or expire when you resume respiration? Well, it's kind of, all right, so this is kind of what I'm getting into. This is kind of getting into the acid-base system of your blood. So if you were to inhale deeply before holding your breath, then will you have the urge to inspire or expire when you resume respiration? Well, you would have the urge to probably not inspire or expire. And what I mean by that is that if you sit there and you hyperventilate, what happens is that your blood will become more alkaline, right? It'll rise in pH. And because you basically just juiced up all the oxygen in your tissues so it can go a little bit longer without a breath. So what I'm trying to say is you normally wouldn't, I guess you would have the urge to not inspire, expire at all. Okay. Explain your results in number 1. Consider what effects lung volume may have on the desire to inspire. All right, so this Herring-Brewer reflex, that's kind of what I just explained there. I do want to see if I can look it up, and I can add anything else to that. I don't remember that term either. Oh, the overinflation of the lung. Okay, so this is a stretch receptor. Not only is it sensed in the respiratory center of your brain, but it's also it's similar to muscles in the fact that if you were to overstretch your muscles will override that stretch and begin to recoil, because it's similar to a compensatory mechanism that will prevent the muscle or the lung in this case from becoming injured by overinflation. Okay, so what I'm trying to say is if we were to sit here and inhale, all of a sudden, like, you're going to reach the total lung capacity, and this reflex is going to come in and it's going to cause you to breathe out completely, right? Like, you could sit here and blow yourself up. I'm not going to do it right now because I'm not going to make a fool out of myself. But basically, you breathe out enough, then it will your body will override that, and you will exhale it out. It'll be involuntary. Okay, if you exhale deeply before holding your breath, do you have the urge to inspire or exhale when you resume respiration? Well, you have the urge to inspire more, because if you haven't been holding your breath, and it's just like me talking right now, and all of a sudden I were to exhale all my breath out, right? Then all of a sudden there's no oxygen in my lungs, there's no oxygen in my blood, yet I'm still living. So all the oxygen that is in my blood is getting used up very quickly, all right, and causing the pH to bottom out in my blood. This will be sensed by the receptor. I keep saying baroreceptors. That's a pressure. I probably mean chemoreceptors. It's same family. I can clean up my delivery there. Chemoreceptors are sensed by the chemoreceptors in my blood, which sends signals to my respiratory center. All of a sudden, I'm going to inhale. Okay, you've probably all seen this in the movies where these people drowned. I know one of the James Bond, one of the first James Bonds that came out with the current James Bond guy, his girlfriend, I guess, drowns, and this is the very end of the movie, because it's a sappy one. And what happens is that she holds her breath underwater for so long, and then I guess the pH in her blood becomes so low, it sends a signal to her brain to gasp for air. However, she's underwater, so the only thing she gets in her lungs is water, and that's kind of how you drown. And it's not like she meant to open her mouth and inhale a bunch of water. No, it's all involuntary. So you can sit there and hold your breath for so long, but it's not like you can make yourself pass out or make yourself, I guess, try to end your life that way, because what's going to happen is your body's going to override that voluntary response through an involuntary mechanism to inhale. And that's kind of how you can get your pH back. People who have panic attacks will hyperventilate considerably, and I guess this will cause them, I'm not sure if that causes them to pass out, but what it can really do is throw off the pH in your blood, right? And when you hyperventilate, you don't move a lot of oxygen, but what you move enough oxygen to supercharge your lungs with oxygen and your tissues, and that will cause your overall pH to increase. And other things can happen there. It can affect other mechanisms in your blood, and they'll usually, that's why they have these bags, and they have barf bags in airplanes, but they also have You've seen people breathe through a bag, in and out, because CO2 is acidotic. So when you are breathing back in CO2, it will lower your blood pH. And I think we're going to kind of probably get into that either this week or next week, but that it's a large reason as to why we breathe. Okay, let me visit the chat. Looks like we're okay on the chat. Moving on. All right. So hyperventilation is an increase in ventilation with no charge to the metabolic rate. I may have just spoken about this. So how long could you, if we breathe, I'm looking at this this table here. There's really nothing. You can hold your breath after hyperventilation. Well, all right. So once we hyperventilate, right, we supercharged our, I'm going to explain this table real quick. So if we were to hyperventilate maybe 16, 18 breaths per minute, the breathing rate after hyperventilation could be, it can go from 12 to 18 or 20 or 24, however fast you can hyperventilate. I would not recommend doing this. You probably start seeing stars or get lightheaded. How long could you hold your breath after a normal quiet breathing? Well, you could probably hold your quiet, maybe 30 seconds, 60, just depends, maybe even longer. How long can you hold your breath after hyperventilating? Well, a hell of a lot longer, because we've supercharged our body with oxygen. If you want to go underwater for a long time, you can sit there and hyperventilate, get all the CO2 out of your lungs, and then replace it with molecular oxygen or atmospheric oxygen, and you can go underwater for a lot longer time. If you were to get on some kind of medical grade happy gas air in the hospital that doesn't have, well, they would have nitric oxide, but if let's say you just get hooked up to like a cannula and you can inhale like pure oxygen, then, because atmospheric air is only like 24% oxygen, and the rest of it's nitrogen. So if you're talking about doing all oxygen, then you can definitely hold your breath for a lot longer. So the answer to number one, after hyperventilating, is your respiratory rate faster or slower than during normal quiet breathing? Well, it's going to be slower, right? Because we've supercharged the oxygen out, and it has to get back to homeostasis, right? So when it gets back to homeostasis, what it does is that it will slow down, and you'll build your CO2 back up. Because if you hyperventilate, not only are you taking in a lot of oxygen, you're also kicking out a lot of carbon dioxide, and your body likes a certain amount of carbon dioxide in your body, in your system, in your blood. So if you were to blow all that out, then all of a sudden it's out of whack and it has to build back up. All right, so number two, I've already touched on this. Why? So discuss chemoreceptors and respiratory drive. That chemoreceptors basically deals with the pH in your blood. So carbon dioxide is more acidotic, right? It's more acidotic. So we don't want to carry a lot of acid in our blood. Smokers will have a little bit more acidity in their blood just because they have more CO2 that's carried, and that's just the way things are with circulation and just the amount of carbon monoxide versus carbon dioxide versus oxygen. Percentages, that makes up partial pressures maybe in the blood. And then respiratory drive is kind of what I explained to you earlier, where it's an involuntary state where you will automatically inhale air if your blood becomes too acidotic. Okay. After hyperventilating, can you hold your breath for a longer or shorter period of time compared to normal quiet breathing? All right. Well, I'm going to let you guys answer that. I'm done beating that dead horse. So chat me something. I'll say it once again. After hyperventilating, can you hold your breath for a longer or shorter period of time compared to normal quiet breathing? I think the guys here in person kind of know the answer, but they'll probably hold off. Yeah. Yep, that's right. Irina, you're right. It's longer. All right. So why? Discuss chemoreceptors and respiratory drive. So basically what happens, what I said is that when you hyperventilate, you're blowing off all the CO2 in your blood, in your body, and your body has to build this carbon dioxide back up. How it does this is by holding your breath, and your body will still go through metabolism. It'll still create CO2, and that CO2 will stay in your blood until you were to exhale it out. Okay, so why do you become dizzy after hyperventilating? Well, it's a pH imbalance in your blood, right? And this pH imbalance is caused by an imbalance in oxygen and carbon dioxide. So we're taking on a boatload of oxygen through hyperventilating in the atmosphere, and we're also blowing off a lot more carbon dioxide than what we need to. And that's why you can kind of get dizzy and see stars. Yeah, not enough CO2. So your pH goes way too high. You're too basic, too alkaline. This is kind of what happens when people OD. Heroin, I think, what it will target. Barbiturates do this too. Barbiturates is like a sleeping aid. When people want to take a sleeping aid and then take alcohol, which are two downers, you put two downers, two depressants together, and it will seize your respiratory center in your brain. It doesn't sense the pH in your body, and then your blood will become too alkaline, and that's another way of suffocating, so to speak, just because you took too much blow, or well, I guess that's cocaine. Heroin, I don't know what smack. I don't know what heroin is these days. I used to know though. Okay. Now, protocol 5. Let's see if any more we can touch on this. Breathe normally 3 minutes, record your breathing rate, then breathe into a paper bag. After completing this, measure your breathing rate for 1 minute. The bag's not going to do anything. If anything, what they're trying to assimilate here is that if you think about it, we're not exhaling our CO2 out. It's like breathing underneath the covers of your bed or something. If you think about it, when you exhale out, you're exhaling out CO2. Well, if you're in a confined space, you're also inhaling CO2 back in your body. CO2 does nothing. Okay, it's a waste product. It's good for plants. Plants like it. It uses through photosynthesis. However, so what we're trying to demonstrate here is that if we breathe through a bag and we are exhaling CO2 and then we're inhaling that same air, we're also inhaling a higher percentage of carbon dioxide. So what happens is when we inhale a higher degree of carbon dioxide, it's going to cause our blood pH to what? Drop. And then our chemoreceptors in our brain sense this, sends signals to the respiratory center to start exhaling or get fresh air. Okay, so now hyperventilate for 1 minute, then breathe into a paper bag for 3 minutes. After completing this, measure your breathing rate. It's not going to tell us anything different. I think I've already explained that. What do you think will happen to your subcutaneous ventilation following a period of rebreathing the same gas? Well, if we're rebreathing the same gas, like I said, we're inhaling more CO2 than what we should. And all that's going to do is increase our breathing more because we're really striving for oxygen at this point. See, CO2 does nothing. It's not like CO2. CO2 is like on the way out. It does not do anything when you inhale it back in. Carbon dioxide or carbon monoxide, CO, will kill you. You probably heard some stories out of Texas where these people were putting their generators too close to their windows, like car exhaust or a generator exhaust, and it's silent. Carbon dioxide, I don't know, you probably can't smell carbon dioxide. Carbon monoxide, you can't. Yeah, I didn't think so. Carbon monoxide, you can't either. And so what happens is it's the silent killer, right? So when these people put their generators next to their windows and it diffuses into the house, what happens is they're just over there breathing, but they may feel lightheaded, right? They may feel lightheaded, and you get a really bad headache, and then all of a sudden you lose, and I'll tell you how this happens. You lose consciousness, you fall, you hit your head, or you just check out over a period of time. over the years, we've probably heard of stories where people were, they decide they want to end their lives by turning the car on and shutting the garage and letting the car exhaust build up in the garage, and they go to sleep like that. So what carbon monoxide does and how it kills you is that, we have oxygen that binds to hemoglobin, right? There's a certain affinity for oxygen to hemoglobin. Carbon monoxide has like 100 times more affinity for hemoglobin than it does oxygen. Okay. So all of a sudden, when you get enough carbon monoxide in the air and you're inhaling it, you're breathing all this carbon monoxide in, and it's competing for the hemoglobin with the oxygen, and it will outcompete oxygen. So what happens is you all of a sudden you have all this carbon monoxide binding your hemoglobin, and it does not unbind. It just binds, and that's it. And by the time you get all the hemoglobin that are practically ate up with carbon monoxide, you start to get your headache, and then you check out. And when I mean check out, you normally pass away through lack of oxygen in your blood. So that's how carbon monoxide usually kills people. Carbon dioxide, CO2, will does not have a lot of affinity for hemoglobin, and that's why actually it's governed by pH in your blood. There is a lower pH in your body, and that's what helps oxygen kick off of the hemoglobin, and then carbon dioxide will get picked up in the hemoglobin in your body. In your lungs, you have a little bit higher pH, and that's what helps kick off the CO2 to exhale out and allows hemoglobin to bind to oxygen in your lungs. Okay, so I think I've hit that one pretty hard. I hope I didn't lose anybody on that. Chat looks good. All right. So after breathing into a paper bag for 3 minutes, does the respiration become faster or slower than during normal breathing quietly? Well, it's going to come faster because when you're breathing through a bag, you're breathing through CO2. We don't want to breathe CO2. We want to breathe atmospheric oxygen. So once we take the bag away, our body is somewhat depleted of oxygen. So that's why we inhale more. All right. The chemoreceptor part, back to this. CO2, carbon dioxide, will lower our pH in our blood. So when we have a lot of CO2 on board, it lowers our pH, and then that sends signals to our respiratory center and our medulla pons area, and it causes us to inhale air or gasp for air. Okay, hyperventilate before breathing into a bag. Is your respiratory rate slower or faster than after rebreathing in the bag or normal respiration? I wish everybody was in person, because I think you all could just answer these questions. We beat this dead, have we not? So I'm going to let you all answer number 3, okay? It's the same concept over and over again. If we hyperventilate, we load up a bunch of oxygen in our body, so we can breathe through that bag a little bit longer, all right? It'll probably help us get back to homeostasis faster, because we're inhaling more CO2 than when we exhale from the previous breath. I sense you guys are rolling your eyes, maybe because it's the same topic, just in a different perspective. Okay, number 4, I'll let you guys work on that. Okay, 63. All right, we're going to get into some anatomy here. This is back to 137, okay? I'm sure you guys remember some of these pictures. There's nothing for me to add here other than study these, all right? Study them, recognize them. These are what the trachea looks like. You have they almost look like goblet. Yeah, they are goblet cells. That's what I thought. They're goblet cells. There's goblet cells in there that help secrete mucus. The pseudostratified ciliated columnar epithelium. It's a huge, it's a mouthful right there. That is just pretty much that houses the villi. I almost wanted to say microvilli, but microvilli is in the GI tract. you have or excuse me, it's probably cilia. It's probably cilia. It's not villi. It's cilia that will help that align the trachea to help expel any kind of foreign bodies and that you may inhale, allergens, such that help kick out, and you can either spit them up or in some cases they go down into the esophagus. Okay, lung. Here's your alveoli, very thin. If you've noticed, very thin. This is what helps diffusion out when we're diffusing oxygen in and carbon dioxide out. So each one of those thin layers, those are pretty much your capillaries, and red blood cells will come in there, loaded down with hemoglobin. And what happens is that your hemoglobin will pick up oxygen and it will kick out CO2. Interesting point here. We had a patient last night. It's very rare, very rare. I've only seen this twice in my career. Not that I've been doing this for 60 years, but we had a malaria patient come in last night. She was been in Zimbabwe for 20 months with her family working on a mission, and she decided not to take the prophylactic medication for malaria. Now, if you know what malaria is, it is a parasite that will live amongst your red blood cells, right? And she was ate up with them. I mean, it's worth almost doing. I've seen it one time where it's not as much, but she had all different forms of it. She had trophozoites, banana form, and ring form. If you know anything about malaria, those are the different stages or breeding stages of malaria. And it's something you just don't see here in Kentucky. You usually see it in Africa or more southern climates, in near the equator. And that's where she was doing her mission work with her family. And that's where they had the netting over their beds to get the block. It comes from mosquitoes, if you do not know. And it's transmitted when mosquitoes will harbor the malaria parasite, and then when the malaria comes and bites you and sucks your blood, it will transmit the malaria into your system, and then it'll build and fester that way. And what happens, I think she's still here. She's still now. Normally they would go to. We had to confirm it through UK. I mean, we knew what it was, but UK likes to do this because we just don't see a lot of this in Kentucky. So they confirmed it. I don't know if it's falciparum, malaria, or I cannot think of the third one. Falciparum is normally the one I've seen in the past, Plasmodium falciparum. However, the point I'm trying to make here with the alveoli is that what happens is when malaria gets into the red blood cell, one of the ways it manifests is that it will cause anemia. All right, and if you remember what anemia is, that's where we are not able to, we're hyperventilating because we have a loss of red blood cells. When the malaria gets into your red blood cells, what happens is that it'll affect the oxygen carrying capacity of the red blood cell. So if you got a malaria hanging out in your red blood cell, it's going to be very hard for that red blood cell to pick up oxygen and move it around. And essentially you get enough of these guys and hanging out, living off you in your red blood cells, it's certainly going to start causing systemic issues, and that's what brought her into the hospital. She'll be fine. She'll be fine. It's not like she's touch and go here, circling the drain or whatnot, but it's something very interesting. We just don't see a lot of it. Okay. It can. Sometimes it can. When there's certain crisis events, what happened, like if she were to exercise a lot, and it drops the pH, then yes, it can cause water imbalances and all kinds.
You feel like didn't we like immune to it?
Yeah, yes. And sickle cell anemia, that's what it is. Sickle cell anemia, this is like, I remember answering a big question about this. It has to do with genetics. Yeah.
I had it before.
Oh, you did? Oh, you've had it?
Yeah.
Yeah. When you were a kid?
Yeah.
Yeah. So I think once you may be able to build up some kind of antibodies to it.
Like most people who live there, when they get bitten, it's not really serious, like it's not crazy, but like most people from like outside who come there,
Yeah.
because like the body's not used to it. So when new kind of.
Yeah, they never seen it before. Yeah.
Like they get.
Yeah, yeah. You get spooked. Yeah, you get afraid. It would be. It would be. Usually, we just don't see it. And
So like it's like normal back there, but
yeah. Well,
yeah.
it's she had it everywhere. You know, you usually have to look really hard, but you didn't have to look at all. I mean, you get on underneath the scope, and the red blood cells have all kinds. She must have had it for a while.
Yeah.
It's like she had it, had the chills, and had the anemic part.
Like fever, like
Yeah, fever.
You feel kind of.
Yeah, chilly.
cold.
Yeah, chilly and cold. And what it does is that it goes through different stages. Like when it starts to reproduce, then I think that's when that's when your immune system is what causes the chills and fever. You know, that's your immune response trying to fight it. And that's what's kind of interesting. Yeah. So when the plasmodium or the malaria kick up and start to spread around, that's where you feel the effects. And you know, it may be like a circadian rhythm, like maybe every 18, 12 hours. Yeah. Oh, I'm sure. Vomit and everything. Yeah. I think it'd be miserable to have. Well, glad you got over it. All right. So simple squamous epithelium, nothing to add there, guys. Simple squamous epithelium is just part of the lung tissue tube, probably normal on the outside of the lung, probably the lung parenchyma. Okay. Now, 64, I think we're kind of getting to the end of the lab. And what I want to kind of go over here, it's just, I'm not going to go over it as much because it's all memorization and it's anatomy. So this is all the different, if page 64 to 65, 66, this is all the different parts of the pig. I'm not sure why they have the whole pig on there on number 66. May just be for review purposes, but certainly try to do some flashcards on the respiratory system. Now, let me see if we have, I know you guys in the past have wanted pictures. And this is all kidney, this is kidney, this is kidney. Yeah, this is old stuff. Okay. I don't think well, actually I do, but it's not. Oh yeah, it is. Okay. I can take one picture, and for you guys in person, if you want to come over here it is right here. This is just a picture of the lung, if you want to take a picture of that. And I don't think I have anything over here worth sending out. Okay. All right. So how are we doing? Are we good? We've been quiet for about a half hour. Are we okay on the chat? I think we're done. Yeah, Raymond, that's what I just 65. Is that what you just? What's 60? Yeah, I have that. I have that in lab. I'm going to take a picture of it and I'm going to send it out. All right, Liz, you wanted to do the quiz, right? So you guys, let's do the quiz because we got a quick turnaround on the quiz this week. So let me look this up. All right, it's quiz 6. All right, so number 2, the amount of air that remains in the lungs after exhaling as much as possible is called, now I'm not going to answer these for you all. I'm just going to tell you what it is so you can have your answers ready when you do it. If you take a deep, question 3, if you take a deep breath as you possibly can after a normal quiet inspiration, what is the name of the volume or capacity inhaled? These are all fill in the blank. And then this is recorded, so I'll be up on YouTube and you can rewatch it and get your answers ready. The specific location that initiates expiration is the, I'm not sure if we went over that. Make sure you look into the specific location that initiates expiration. That may be on like a pre-lab or in the lab somewhere. I want to say it's respiratory center. If you get somewhere close, obviously I'll give you credit. Central chemoreceptors are sensitive to pH. I want to tell you that one. That's number 5. Number 6. What is the name of the mechanism that prevents you from inhaling too deeply or damaging your lungs with overinflation? Well, that was that HUR. Yeah, I can't pronounce it. HUR reflex, Hero-Brain reflex. That must be the 2 dudes that founded it. Carbon dioxide, number 7. Carbon dioxide directly stimulates which chemoreceptors? I'm not sure what we want to go there. Chemoreceptors are chemoreceptors. Probably the brain chemoreceptors. Double check me on that. When you hyperventilate, pH will increase. When you hypoventilate, CO2 levels, well, I can't keep answering all these. If you hyperventilate, CO2, if you hyperventilate, you're not moving CO2, you're not moving air, but you're still metabolizing. So if you're still metabolizing, you're still creating CO2, but you're not breathing it out, which means if you're hyperventilating, then CO2 does what? It should build up. As CO2 levels increase, breathing rate will increase because you want to blow off the CO2. Hopefully you guys are getting this. Like if I see you if everybody was in person, I get like nods or don't know, and it's just like talking to a screen. All right.
So hypoventilate, it increases the pH, and hyperventilate.
Hold on. Wait, what's now? Hypo will decrease pH because it increases carbon dioxide. When we have higher levels of carbon dioxide, it will drop your pH because it's acidic. Carbon dioxide is acidic.
Okay, makes sense. Thank you.
No problem. Glad you asked. Any other questions? Okay, and I didn't do question 1. Question 1, it's going to want you to find the expiratory reserve volume. It's going to give you the reserve volume. It's going to give you tidal volume. It's going to give you vital capacity. And it wants you to find the ERV. That's number 1. And if these are randomized, then you're going to get them in different stages. So are we okay? You guys cool? Okay. If you got any questions, I'm sure you'd let me know in class. I guess maybe everybody just like puts me on mute and walks away and watches this later. I don't know. I have no idea. I'm going to start recording.